When NASA finally held its long-awaited press event to reveal the full set of 3I Atlas images, I listened very carefully. I paid attention not only to what they said, but to what they chose not to say. They showed the new smudges from SOHO, some faint signatures from Lucy, a soft halo from Maven, and the same teardrop-like Hubble frame we've all seen before. But during the entire 45-minute presentation, something strange happened. They never addressed the one feature of 3I, Atlas, that should have been the centerpiece of the entire discussion. They never mentioned its size, not once, not in passing, not as a footnote, not even as a cautious aside. And that omission is perhaps the most astonishing part of the whole event. When we analyze an interstellar object, size is not a trivial detail. It is the foundation upon which every other calculation rests. How much material is ejected? How fast is the gas flowing? How dense is the nucleus? How bright should it be? How does sunlight affect it? How quickly does it rotate? How should it accelerate? How many jets can it sustain? How long can it survive its approach to the sun? Every single one of these depends critically on size. Yet NASA avoided the topic entirely. And based on the available data, the Webb infrared constraints, the Maven hydrogen halo, the high-rise brightness profile, the scattering efficiency 3I, Atlas appears to be enormous. A conservative estimate places it at 5 kilometers across. It could be larger. This is not a minor deviation. It is a fundamental and extraordinary anomaly. To appreciate how shocking this is, consider the scale. Oumuamua, the first interstellar object, was roughly 100 meters. Borisov was about 1 kilometer, but Atlas appears to be 5 kilometers or more. That means Atlas is 1,000 times more massive than Borisov and 1,000,000 times more massive than Oumuamua. We have only observed 3 interstellar objects. There should be a natural distribution. Mostly small ones, a few medium ones, and extremely few giants. Yet the third object we detect is the largest by a factor of 1,000,000. This is statistically absurd. It defies the expectation that we would see 1,000 smaller bodies before stumbling upon a giant. If you roll a die, you expect all numbers to appear many times before seeing 6 1,000 times in a row. That's the situation with Atlas. And that is why size is not a detail, it is the puzzle. We can frame this probabilistically. If interstellar space is filled with debris, fragments of planets, comets, and asteroids from distant star systems, then the most common objects should be the smallest. They are easier to eject, they drift more freely, they exist in far greater numbers. But Atlas violates this expectation not just slightly, but violently. Imagine the first 2 raindrops that fall on your hand are tiny, gentle droplets, and the third is a fully formed iceberg. Would you call that normal weather? Or would you ask, what kind of sky could produce such a thing? That is the question NASA avoided. A 5-kilometer nucleus is not something you casually eject from a planetary system. The gravitational energy required to launch such a mass into interstellar space is enormous. Planetary scattering can do it, but only under extremely specific configurations. A binary star system might do it, but the mass distribution must be perfect. A planetary collision could eject such a fragment, but the geometry would need to be exact. In every scenario, the probability is extremely low, which means Atlas either comes from an extraordinarily rare environment, emerged from an extreme catastrophic event, or was produced by a mechanism we do not yet understand. But instead of exploring these possibilities, NASA avoided the topic entirely. What we received from the event was a collection of images, most of them fuzzy, incomplete, and lacking scientific context. A blurry SOHO frame where the comet is barely a pixel, a faint glow in the Maven UV camera, a smudged cloud from HiRISE, a sideways tail from Punch, a thermal hotspot from SphereX, a few dots on a Webb spectrographic plot, a dusty cocoon from Hubble. Interesting, yes, but none of them address the central questions. None explain how an object this large entered our solar system. None explore its rarity. None contextualize the statistics. None mention the size. Another unusual detail NASA avoided is the trajectory. 3I Atlas arrived almost perfectly aligned with the plane of the planets. This alignment allowed so many spacecraft, Hubble, Webb, SOHO, Stereo, Lucy, MRO, Maven, Punch, even rovers to observe it. But this alignment is improbable. Only about 1 in 500 interstellar objects would naturally follow such a convenient path. NASA presented this as luck, almost something to celebrate. But scientifically, the correct question is, why is this so rare, and why did it happen now? Again, the anomaly was simply ignored. Every major discovery in science has begun with something that didn't fit. Mercury's orbit didn't fit Newton until Einstein. The ultraviolet catastrophe didn't fit classical physics until Planck. The photoelectric effect didn't fit Maxwell until quantum mechanics. Dark matter didn't fit galactic rotation curves and still challenges us today. When nature presents an anomaly, the role of science is not to hide it or treat it as inconvenient. Our role is to investigate. And 3I, Atlas presents multiple anomalies. Its enormous size, its nickel without iron composition, its tightly collimated jets despite rotation, its alignment with the planetary plane, its unexpected outgassing far from the sun, its inconsistent brightness across wavelengths, its shape and dust behavior. The size alone challenges our understanding of interstellar object formation. Combined with everything else, the case becomes even more compelling. Yet NASA avoided these topics entirely. To be fair, I do not believe NASA is intentionally hiding information, but NASA is a bureaucracy, not a philosophical institute. Bureaucracies prefer safe answers. They avoid uncertainty, avoid speculation, avoid statements that might create public confusion or scientific controversy, and the size of Atlas leads directly into those uncomfortable territories. Acknowledging the size is acknowledging that our models may be incomplete, and acknowledging model incompleteness means admitting we don't fully understand this object. That discomfort is exactly what drives progress. One of the strangest features of 3I, Atlas, is its chemistry. We detected nickel but almost no iron. This is unheard of. Nickel and iron are produced together in stars, and in every comet, asteroid, or meteorite we have studied, iron is more abundant. The only place you see high nickel materials with very little iron is aerospace-grade nickel alloys. I am not claiming Atlas is artificial, but I am saying that the combination of enormous size, unusual chemistry, rare trajectory, tightly collimated jets, extraordinary mass, and high water production far from the sun demands openness to possibilities. NASA did not mention the nickel anomaly, nor connect it to the size anomaly. But these anomalies do not exist in isolation. They form a picture, one far from simple. Based on current observations, Atlas rotates roughly every 16 hours. If that is true, then the jets should wobble or spiral with rotation. But they do not. They remain straight, stable, tightly collimated like laser-thin beams of gas. This is not typical comet behavior. Combined with the massive nucleus, it creates a paradox. A large, slowly rotating comet should produce broad, curved jets, not narrow, straight ones. Yet Atlas does. This is why jet collimation was one of the anomalies I highlighted earlier. NASA did not mention it. Let me stress again. I am not arguing that 3I, Atlas, is artificial. I am arguing that it is not yet understood. If it is natural, then the natural processes that formed it are unlike anything we have previously encountered. It may have originated from a catastrophic planetary collision, a volatile-rich moon shattered by a passing star, a Kuiper Belt analog far more massive than ours, a disrupted mini-Neptune, the frozen mantle of a destroyed water world, or a tidal stripping event in a binary system. All rare, yet the size alone forces us to consider them, and the best observations are still ahead of us. On December 19th, Atlas reaches its closest point to Earth. That is when Hubble, James Webb, ground-based arrays, infrared telescopes, radio observatories, spectrographs, and amateurs worldwide will all observe it. We may finally measure the nucleus directly. We may resolve the jets in high detail. We may identify volatiles never seen before. We may detect anisotropic heating. We may observe rotation signatures or fragmentation events. Whatever we find, the size anomaly will remain the central mystery. Ignore the size, and we risk ignoring the truth. In science, it is easy to believe we understand everything, but the moment we feel certain, we stop learning. 3. Atlas is not a threat, not a crisis, not a danger. It is a gift, a messenger from another star system, a clue to how material forms and evolves in environments far beyond our own. But for this object to fulfill its purpose, we must ask the questions NASA avoided. Because the size is not just a number. It is the clue that may rewrite our understanding of interstellar geology, planetary formation, and cosmic evolution.